We're going to summarize where we stand right now with graphs of polynomial functions, and I'm trying to project this entire summary sheet in one view so it's easier to take in. So graphs of polynomial functions. Let p of x be a polynomial function of degree n with leading coefficient a sub n, so any polynomial function at all. What's important is that you understand that we know what the end behavior is for that function. It will match x to the n if the lead coefficient a sub n is positive. It will match minus x to the n if the lead coefficient a sub n is negative. Now by end behavior, let's just look at a couple examples. We know with degree 3, x cubed, the x cubed graph looks like this, minus x cubed looks like this. For any cubic polynomial, the end behavior is going to be one of these two types. Now, in the middle, there can be wiggles in the graph, so a graph could possibly go up, down, up, but the end behavior will either match x cubed or the end behavior will match minus x cubed. So this isn't about wiggles in the middle, this is about what happens at the extremes when x approaches infinity or minus infinity. Same thing with the degree 4 polynomial. The end behavior will always match x to the 4th or minus x to the 4th. So I think you can see with an even degree polynomial, the end behavior is either f of x approaches infinity at both ends or minus infinity at both ends. And you might have a wiggle like that with degree 4, or you might have a wiggle like that with degree 4, but the end behavior matches one of those two. Any horizontal line crosses the graph at most n times. So what does that mean? Well, here's some examples of degree 2, degree 3, and degree 4. Degree 2, I can find a horizontal line that crosses that parabola twice. Degree 3, I can find a horizontal line that will cross the graph at 3 points, but maybe fewer. For instance, a horizontal line up here will only cross that graph once. When I have degree 4, I can find horizontal lines that will cross the graph possibly 1, 2, 3, 4 times, or fewer, right? If I place the horizontal line in this position, I'm only going to cross the graph at two points. The graph has at most, maybe fewer, n minus 1 turning points. In calculus, these are called local maximum, local minimum points. Now, what's a turning point? A turning point is either the bottom of a valley on the graph or the top of a hill on a graph. The turning points are where we change from decreasing to increasing or from increasing to decreasing. So n minus 1 just means there's one fewer turning point than degree at most. So for degree 2, you can have at most one turning point. For degree 3, you can have at most just 2 turning points. For degree 4, you can have at most 3 turning points, maybe fewer. And just one more thing I want to say about this turning point idea. Personally, I like to think of the curve as having increasing and decreasing portions, meaning you have a portion that goes down here and a portion that goes up. The number of increasing and decreasing portions of the graph can match the degree. And you change from increasing to decreasing or decreasing to increasing at a turning point. So for degree 2, if I go down, up, 1, 2 matches the degree. For degree 3, I go up, down, up, 1, 2, 3 can match the degree. Of course, it could also be less than that, right? So 1, 2, 3 increasing, decreasing portions, just 2 turning points. Degree 4, 1, 2, 3 turning points, possibly, but increasing, decreasing portions, you can go down, up, down, up, 1, 2, 3, 4. The decreasing, increasing portions of the graph can be equal to the degree or less. And then a few more points. The domain of any polynomial function is all real numbers. So we never have to remove values of x from the domain of a polynomial. We like polynomial functions in math. We like them because their domains are always all real numbers. The graph of any polynomial function is continuous. The word continuous means that there are no breaks, no asymptotes to the graph. And finally, finding exact values for x-intercepts and turning points may actually be impossible. And we don't have to worry about that in our class. But in the last example that I graphed, I didn't really hit the turning points exactly. I just sort of approximated them. And it can be very difficult to find, and sometimes it's impossible. So that's our summary. Now, next video we continue on with polynomial functions on part 3. This is just our part 2 summary of where we're at the moment.